Hi, my name's Seth Kitchen, and I'm going to be teaching you guys about sets. Okay, just the general thing about sets is when you're comparing sets to something in the real world, the easiest way to do it is compare it to a club. You know, not like the club where you mace someone back in the Middle Ages, but, you know, the kind of club that you have in a high school, elementary school, middle school, you know, chess club. That was a great club, right? There are lots of ways people talk about sets, but the major thing is one single letter capitalized with a big line running through it. So basically, if you're looking at a math problem and you see some big letter and you're like, what the is that? Okay, so let's talk about one, for example. The big Z with the big line going through it where you're looking at it normally and you're just like, what is that? Well, it means it's the set of all integers. So if you're talking about 0, 1, 2, 3, 4, 5, 6, you know, keep going like that. You can also go in the opposite direction. Let's go 0, -1, -2, -3. Those are all integers, but the only thing that's not in that are the irrationals and the rationals. So you can't have 1/2. That's not contained in Z. So let's also talk about what contained means. Basically, you can designate it by using a epsilon. So if you have x epsilon z, this means that x as a variable is contained in the set of integers. So what does this mean? This means that x is only allowed to be -1, -2, -3, and keep going that direction. You can also have 0 or 1, 2, 3, or keep going in that direction. You just can't have the square root of 2, 1/2, -1/2, so on. And that's a different set. Also, if you're talking about square roots, right? Well, you can't have the square root of negative number. People say that all the time. You know, if you're talking about the domain and range in calculus, most of the time, you'll have the square root of -1, and you'll be like, oh, well, that's not continuous, and because that's not allowed, right? Well, if you're in the set of imaginary numbers or complex numbers, it's designated by a big C. So if you have x is contained in this big C, basically you can have a square root of -1 or -2 or something, because we all know this translates to some derivative of I, not derivative like calculus, but you know, a version of -1. So let's get back to sets. Most of the time when people talk about sets in the world, they're going to be like, oh, I have a baseball team, and it has a set of players on it, or a collection. You know, a set is a collection. It's a very specified collection. Some examples of sets are the 1977 to 78 University of Michigan basketball team. Yeah, how about that? That's a really specific example. But it can also just be something like, you know, the set of rooms in a building. You know, I have 2 bedrooms, 2 baths for all you real estate people out there. But that's also a set. All those rooms are in a designated, you know, boundary of a house. And you can get even more specific into that set, the bathrooms or the bedrooms, you know. And related to math, you can have a set of circles in a given plane. So as a challenge to you, if you don't know what a collection is, you know, well, everyone knows what a collection is, but to practice this concept of sets and collections, you can think of more collections you can think around you. Now, what is a roster name for sets? Basically, it's a way of representing the sets. Okay, basically what you're going to use in a set is curly braces. If you don't know what this is on your keyboard, it's shift and then a bracket. You know, it's very curly. But you're going to have a curly bracket that is open to the right, and you're going to include everything that's a member of the set. So let's say we're talking about actors that appeared in Harry Potter. Well, you would have an open brace, and you would have Daniel Radcliffe, and then you would have Emma Watson, and ... all the rest of the characters in Harry Potter, and then an end brace. And that would be your set. So if you're talking about this later on, you can say, oh, Daniel Radcliffe is contained in the set of Harry Potter actors and actresses. Okay, and let's talk about this with math now. So you could have the integers, right? So a way you could represent this is a open curly bracket to the right, and then after the smallest number would be negative infinity. So you would actually want to start with a dot dot dot, and then you could put some numbers in there like -3 comma -2 comma -1 comma 0 comma 1 comma 2 comma 3 dot dot dot, and then have your end curly bracket. And basically what you can talk about with sets is you're never going to be specific enough if you're working with a large set, an infinite set. You can't just keep writing numbers forever, or your hands will get tired, they'll fall off, and you'll be like, oh my god, this isn't math anymore. This is like me dying. Basically, you can just do a dot dot dot, and that'll solve your problem. Also, you can have equal sets. Set that contains authors, right? Well, in the set, you're going to have open curly brackets Shakespeare, comma, Mark Twain, comma, dot dot dot, more authors, in curly brace. So then you have another set next to it that has curly bracket Shakespeare, comma, Samuel Clemens, comma, and then the same stuff that was in the first set as the dot dot dot, you know, so you say dot 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 again. Basically, this is the exact same set because Mark Twain is Samuel Clemens. It's his pen name. So basically, it's the same number. And what am I trying to talk by this? Basically, I'm saying you don't have to have the exact same format of an element in a set when you're comparing them. So an example of this in math would be a set that contains only 0, 1, and 2. Well, this would be curly bracket 0, comma 1, comma 2 in curly bracket. This is also equal to curly bracket 0, comma 1, comma 1 plus 1 in curly bracket. So this 1 plus 1 we all know is 2, and that therefore the sets are equal. You can also do 3 minus 1 as the last element, or 4 plus 3 modulo 5 in the last element. You know, you can go crazy with this stuff. Also, if in a roster, and remember when we're talking about roster, we're talking about this curly bracket notation. If you have a curly bracket 2, 3, 4 in curly bracket, this is going to be the same set as curly bracket 2, comma 3, comma 3, comma 4, comma 4, comma 4, comma 4, you know, in curly brace. It's going to be the same because you have the same elements, they're just listed multiple times. Basically, you can list an element multiple times, it's still going to have the same value. It's not important. This notation of dot 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 is called improper roster names. Even though it's improper, it's generally accepted as a mathematical slang. And we know that since we can't write all of the numbers, it should work pretty well. Just try and be specific. It's also important to understand if I have a set of just the number 0, that's a set. It's just, I know it only has one element, but it is a set. And actually we call a set with one number a singleton set. A singleton set has one element. Okay, let's try this. We're going to have a curly brace, and then another open curly brace, 0, in curly brace, comma, open curly brace, 0, comma 1 in curly brace, and then in big curly brace. Basically, you have two sets that are a member of an entire set. So if we have the set all real numbers represented by big R, also contained in this set is the set of integers. It just has more to it. So you would have in your curly brace for all real numbers, you would have Z, comma, more items. So you could have Z, comma, the square root of 2, comma, dot 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 in curly brace. Because then that set is contained in that total set, which is the real numbers. Another tricky concept to understand is the fact that one element is not equal to a set, even if they're the same value. Let's say we have the element 0. So let's just say 0 is not equal to open curly brace 0 in curly brace. And the reason for this is you need to think of it back to our club example. Let's say we have a person in it called Charles. Charles is not equal to open curly brace Charles in curly brace. Because even though Charles might say that since he's the only person in this club that he is the club, that doesn't mean that he necessarily is. That Charles has a lot of friends, right? The club doesn't have a lot of friends because there's no one in the club except Charles. So they're not equal in that sense. Also, if Charles is like 7 years old, that doesn't necessarily mean the club is 7 years old. You know what I'm saying? They're two different things. You have to think of them as two separate entities. Is Charles a member of Charles? See, you can't have Charles being contained in Charles because Charles is Charles. It just doesn't make sense. So what happens if we just have open curly brace and then end curly brace? We call this the empty set. It has nothing in it. But mostly the empty set has a standard name derived from phi. It's a Greek letter. It has nothing in it. It's empty. It's void. If you compare any number to it, that number is not going to be contained in this empty set. A tricky concept to understand is this empty set, the null set, is this a singleton set? Well, it depends in what context. If you have phi, this is not a singleton set because it has nothing in it. There's no element. To be a singleton set, it must have at least one element. Well, if you do big curly brace, then phi, then end curly brace, it is a singleton set because it contains one element. It's the set of the null set. There's another thing is there is only one empty set. If there were several empty sets, we would refer to them as an empty set, but it's the empty set. So basically, the way you graph a collection or set is to just plot points, put what their value is, and then draw a circle around them. This will include all the numbers in the set.